Now, as we're looking at bonding, we'll see that there are times when we can move electrons around in our molecule and still come up with good Lewis forms. Here we sometimes say that the electrons resonate around the molecule, so we need to take a look at this resonance phenomena and then use formal charge to determine which Lewis forms are the best. Now, when more than one valid Lewis structure can be written for a particular molecule, we'll have to evaluate the various forms and see if any of them disobey our octet rules. If everything obeys the octet rule, then we start looking at formal charges. But first, let's just talk about resonance. In nitrogen trioxide, we have 24 electrons. We can write our Lewis dot structure with a double bond between nitrogen and oxygen, and then single bonds between nitrogen and two other oxygens, and then distribute our electrons so that we have octets around all of our atoms. If we move electrons around, we can push electrons from one of the oxygens onto the nitrogen and then push the double bond electrons onto the oxygen with only 2 electron pairs and end up with another Lewis structure where the double bond is now between nitrogen and a different oxygen. And we can do that another time so that the electron pair is between nitrogen and the third oxygen. Here the electrons are moving around the molecule. They're resonating. All of these Lewis forms are equivalent. They are all valid Lewis structures. The true molecule is an average of these three forms. It's what we refer to as a resonance hybrid. The electrons are really delocalized rather than localized between nitrogen and any single oxygen. They're delocalized over the entire molecule. They're able to move around so that we actually have about a 1.5 bond length between nitrogen and each oxygen. So when we can write more than one Lewis structure for a molecule, we have to evaluate the Lewis structures that we've written and determine if any of them are better than the others. If we have multiple Lewis forms which are all decent, and then we go ahead and average them together to come up with our resonance hybrid. Remember, atoms and molecules try to achieve formal charges as close to zero as possible when we're evaluating Lewis structures. And if we have formal charges, negative formal charges are expected to reside on the more electronegative atoms. Positive formal charges should reside on the more electropositive atoms. Now, in order to calculate a formal charge, we first take the number of valence electrons on the free neutral atom that we're looking at. Then we subtract the number of valence electrons assigned to that atom in the molecule. The way that we assign electrons to an atom in a molecule is by first assuming that lone pair electrons belong entirely to that particular atom in question, so we can add all of our lone pair electrons. Shared electrons are divided equally between the two sharing atoms, so we can either divide the number of shared electrons by 2, or just count the number of covalent bonds. So we take the sum of the lone pair electrons and 1/2 the shared electrons. We subtract that number of assigned electrons from the number of valence electrons on the free neutral atom. And then we check to make sure that the sum of our formal charges for all of the atoms in a given molecule equal the overall charge on that species. So let's go ahead and calculate formal charges for each of the atoms in this phosphorus fluoroxide. First, if we look at phosphorus, it has 5 valence electrons. There are 4 covalent bonds, so we can subtract 4 from 5 to get +1 for the formal charge on phosphorus. We could also count up the number of shared electrons, 2, 4, 6, 8, divide that by 2 to get 4 to subtract to get our formal charge on phosphorus. Next, oxygen has 6 valence electrons. So we have 1 shared pair and 3 lone pairs on oxygen. So that's 6 electrons from the lone pairs plus 1 from the shared pair to give us 7. 6 minus 7 is -1. All of the chlorines are equivalent here, so we only have to calculate the formal charge for chlorine once. Chlorine has 7 valence electrons. There are 6 electrons on each chlorine from lone pairs, plus 1 electron from the shared pair, for a total of 7. 7 minus 7 is 0 formal charge on chlorine. The net charge is 0 on this molecule. There's a formal charge of +1 on phosphorus, -1 on oxygen, which sums up to 0. Now, if we have non-equivalent Lewis structures which exist for a species, those with formal charges closest to 0 and with negative formal charges on the most electronegative atoms are considered to be the best Lewis structures describing the bonding in a particular molecule or ion. So here we have 2 different Lewis structures for carbon dioxide. In one Lewis structure, we have a triple bond between carbon and oxygen and a single bond between carbon and oxygen. All elements have octets of electrons. All of our electrons are utilized. In another form, we have double bonds between carbon and each oxygen. Again, all octets are satisfied. All of our electrons are utilized. The form on the left with the triple bond has formal charges. The form on the right does not. Therefore, the form on the right is the better of the Lewis structures because of the lack of formal charges.